x is greater or equal to 1. So I went ahead and just plugged in 1, 2, and I saw that it kept getting smaller, so it was approaching 0. And then I went over here and computed. So I went ahead and found an integral, or went ahead and evaluated it. I got negative x to negative 1, which is negative 1 over x. So then I went ahead and evaluated. So I had negative 1 over 10 minus a negative 1, which ends up adding 1. So each time I evaluated it, it was always close to 1, which means that, which I saw something there, but then I went ahead and did the, I guess you could say, the definition. And I knew that negative 1 over n approaches 0, and 1 was just 1. So the area was always approaching 0, which was just that I was computing.
Where did that 1 over x squared come from? Right underneath the f of x? Yeah.
Well, f of x equals 1 over x squared. So f of x dx.
Other questions for him? You got Raven, what are you working on?
I might have missed you say it, but how did you get 50 after 20?
Oh,
This one?
yeah, I gave in the problem, I said, give me the integral from 1 to 10, give me the integral from 1 to 50, give me the integral from 1 to 100. Because what point am I trying to make, Gerardo? You said it. You said
Yeah,
it.
it's closer to
What happens as the top number gets bigger and bigger and bigger? What happens to the integral?
I guess small, well, yeah.
It's closer and closer to not 0.
Well, the
function
area,
is closer
the
to-
area, the area approaches, or gets closer to 1.
Correct. The area gets right, and that's the whole point. We can't integrate from 1 to infinity. That makes no sense because infinity isn't a real number. You can't plug it in, right? When you integrate something, you plug the endpoints in, you subtract. But you can't if it's infinity, so what do? You say, well, let this number get bigger and bigger and bigger and ask what happens. All right, questions for me? All right. Now, let me re-emphasize that point, because if you understand this point, you understand everything there is to understand about these guys. Right, 1 over x squared. At 1, it's at 1. At 2, it's at 4. At 3, it's at 1/9. All right, so if we ask what's the integral from 1 to 50, we're asking for this area, right? And he did that right here. It's a no-brainer. Integral 1 over x squared. What's the antiderivative of 1 over x squared? Negative 1 over x. What do you plug in? 50 at the top, 1 at the bottom. Negative 150 minus a negative 1 is 1 minus 1 over 50 is 49/50. You can almost guess right there that the whole integral. So what's the point? The point is this region is unbounded, right? The region is unbounded. That doesn't mean the area is infinite. Now that seems a little bit strange, right? If the region's unbounded, why wouldn't the area be infinity? Well, think of it like this. Suppose we integrated all the way out here and that area was 1. It's not, right? We figured out it's 49/50. But suppose then we integrated out here from 50 to 100 and that area was a half. And from 100 to 150, that area was a fourth. And from 150 to 200, that area was an eighth. You with me? What happens if I add 1 plus a half plus a fourth plus an eighth plus a 16th plus dot, dot, dot. Is that equal to infinity? I'm adding up infinitely many numbers. Does it have to be infinite? No, because what is 1 1/2? Well, that's 1 1/2, right? What if I add 1? It's 1 3/4. What if I add that eighth? It's 1 7/8. What if I add that 16th? It's 1 15/16. So if I add up these infinitely many numbers, what do I get? 2. So it's perfectly possible to add up infinitely many numbers and not have infinity for your answer. Right? Austin, you look doubtful.
No, it makes sense.
You trust me?
Yeah.
1 1/2, 1 3/4, 1 7/8, 1 15/16, 1 32, 1 32nds.
Right, it's just
1
approaching 2.
63 64ths. This number never makes it to 1.
Right.
Because what I'm doing is I'm walking half the distance to the door, right? If I take infinitely many steps, do I have to get out the door? No. I go half the distance. I go half the distance again. I go half the distance again. I'm taking infinitely many steps, but I'm never going to leave the room. So you can take infinitely many steps and not cover infinite distance. Most people do that in their whole life. This is the same concept. This area under here is unbounded. It's an unbounded region, but that doesn't mean the area is infinite. So what makes sense? What makes sense is to do this. Integrate from 1 to n. And then ask what happens as n goes to infinity. And so that's it. We did 1 to 10, we did 1 to 50, we did 1 to 100 to get an idea. And it's 9/10, 49 50, 99 100. I'm pretty sure the answer is 1. But to get the answer, he's got to integrate, take the limit as n goes to infinity of the integral from 1 to n. Same integration, negative x to the negative 1 from 1 to n. Plug it in. What does negative 1 over n go to as n goes to infinity? It goes to 0. Therefore, the whole thing goes to 1. Good? You understand that? You understand infinite improper intervals. Yeah.
So the area would never reach 2?
Yeah, this graph doesn't fit my numbers that I made up. I was just saying, suppose this is some function f of x, and you found the area from 1 to 50, and it turned out to be 1. And then the area from 50 to 100, just that area, turned out to be a half. And the area from 100 to 150 turned out to be a quarter. Then the area would be 1 plus a half plus a fourth plus an eighth plus dot dot dot, and it would never get to 2, would it? Like I said, that concept of adding up infinitely many numbers and not getting infinity messes with people's minds. Because you're thinking, well, if I add 1 plus 1 plus 1 plus 1, yeah, that goes to infinity, right? Because that one's 1, those 2 make 2, those 3 make 3, well, it's growing without bound. But by adding half the distance to the door each time, 1 foot from the door, I'm half a foot from the door, how far am I traveled? Add up the distance traveled if you want. The distance I traveled the first time was 1 foot, the distance I traveled the second time was a half a foot. I'm never going to get to the door because I'm cutting my distance by half each time. So it makes sense mathematically and it makes sense from a physics point of view. I'll give you an example sometime today of one that doesn't make sense from a physics point of view. So right about the time you get to understand it, I'll confuse you. Okay. What you guys got? Here?
Yeah.
You got the antiderivative, right?
Yeah.
X to the negative 2 is negative x to the negative 1. Right? So then he plugs into this. So he gets negative 1 over n minus a negative 1. So that whole thing is basically 1 minus 1 over n. Right? Now what happens is n goes to infinity. What's 1 over n go to when n is getting bigger and bigger and bigger? Getting smaller and smaller and smaller, right? So he's got negative 1 over n plus 1, but the 1 over n is going to 0. Therefore, the limit as n goes to infinity of 1 minus 1 over n is going to 1.
I'm still kind of confused how it went from the limit from n to infinity to n to 1. How did that become 1? Because at the end of the limits, aren't you supposed to put the two that are under the limits on the outside, right?
Yes, and he did, n to 1. 1 to
Oh,
n.
okay.
The limit only has to do, here's 1, here's n. So he's integrating from 1 to n of that function, right?
So
But then he's taken the limit as the n goes to infinity.
Okay.
So those are two totally different things. First, don't think about the limit, don't let it confuse you. Just integrate what is this function from 1 to n.
Okay.
Then, once you've done that, evaluate what happens as n goes to infinity. If it
understand.
goes to a number, then the area under that curve is finite. If it doesn't go to a number, then that area under that curve is infinite or unbounded. Good job, Jordan. Other questions? We good? Okay, Johnny?
I try to integrate this. At least definition. I found the definition of this. So I'll put n as my as going to negative infinity. And got that. And then I found the definition of this one too. So that's negative infinity. So I'll put limit as it goes to negative infinity, and then it goes to 0, because you can't just skip all the way to infinity because they're both not numbers. And then I added that plus limit as n goes to infinity. And I put my infinity as 0. And I put my n as, no, I put my negative, well, I put 0 right here, and I put my negative infinity, I mean my infinity as n.
So basically all you do is just break your rules.
Yeah.
And this is 246.
What you got, Randy? Look where you.
So where at the top where it says that integrals into the limit of that integral, so is that a formula? Not a
Yeah,
formula,
it's
but
a definition. That's exactly right. The question asked you, make up a definition. We have a definition for 0 to infinity. The limit as n goes to infinity of the integral from 0 to n. This one said, well, what if it was from negative infinity to some number? What are you supposed to do? You're supposed to say, well, I can't plug negative infinity in, right? So make it be n and take the limit as n goes to negative infinity. What's another perfectly good way to write a definition for that means the exact same thing? Suppose you wrote the limit as n went to positive infinity. How would he change the endpoint of the integral?
Right.
Yeah, if you write right underneath that. Right underneath that, right, equals the limit as n goes to plus infinity, and then do an integral, and tell me what would the endpoints be, anybody? No, because you don't want to move that a. Oh, well, actually, I guess that would work. Right, let's see, that would be same as negative the integral from infinity to a.
It did not have that.
Let's see, so we're trying to figure out, what we've got is negative infinity to a, right? So we've got, here's negative infinity, and here's a, and we're trying to figure out that area, right? So everybody understands this, the limit as n goes to negative infinity, you're just, right, you're just stopping it at n, and then letting n go to negative infinity. Makes perfectly good sense. Now, I switched it and said, well, what if n went to positive infinity? What could the endpoints be? If we do a to n, then we'd be doing out here, Johnny. You with me? And I don't want this area out here. But how could I write those endpoints? Negative n, right? It's the same thing. So the point is, it's just, if you want to let n go to positive infinity, then, well, negative n is going to negative infinity, right? Same thing down here. This could have been written. Nothing wrong with the way he wrote it. Is what he did is he said, okay, here's my function. Maybe it looks like this. I'll integrate from 0 out to n. And I'll integrate from 0 out to negative n. No, n to 0. And I'll let this n go to negative infinity. And I'll let this n go to positive infinity. Perfectly valid. That way he gets all of this area and he gets all of this area and adds them together. But it would also be okay to break it up, look at it like this and say, well, let's integrate from negative n up to positive n, right? And then let n go to infinity. That way this one's going to positive infinity. Since n's going to infinity, negative n's going to negative. Anyway, those are just definitions for how to compute improper integrals. All right, who's up? Scorpio, show us 247.
All right, 247. For the first part, they wanted me to graph this right here. 4 over x minus 1 squared. This is going, right here is going to make it undefined if you plug in 1 right here. So we have the asymptote at 1, so it's going to go like this. Yeah, then they want me to do the integral of this right here. And the integral of this is the integral of 4 over x minus 1 squared is negative 4 over x minus 1. And so once I got that, I plugged in 100, or I plugged in 2 and 100 for x, as you see right here. And I get negative 4 over 99 minus negative 4 over 1, and 2 minuses equal a plus. When I add them together, I get negative 4 over 99 plus 4. And my answer is 4 minus 4, positive 4 minus 4 over 99. And part 3 is almost the same thing, it's just a bigger number, 100,000. I did the same steps, and I got negative 4 over x minus 1. And I plugged in 1,000 and 2 right here into these numbers. And when I plugged that in, negative 4 over 99,999 minus negative 4 over 1, 2 negatives equal positive. I get negative 4 over 9,999 plus 4, and I just rewrote it right here. I thought we wrote that one. And number 4 is the integral of 4 over x minus 1 squared. And then different integral is infinity and 2. I plugged it in. What I got when I plugged in infinity, I ended up getting 0. Because if you take 1 away from infinity, it's not really nothing. Over 4, it'll make it go to 0 because it's a negative number. And then I got 0 minus negative 4 over 1 to minus signs equals a plus. I just got 4 on that. And on part 5, my integrals was negative infinity and a. And a was a number greater than 1. So I did that. When I plugged in infinity, I got 0 minus 4 over a, and I got 4a. I'm not really sure about this one, though.
Would you leave it as a minus 1?
I wasn't real sure about this one.
What was the
This
question?
was just my guess. I said I wasn't real sure if this one was right, this last one. I just,
Well, let's just check. You plug in, when you put infinity in, I agree, you're gonna get out 0 minus a -4 over a minus, wouldn't it be a minus 1 when you plug in the a?
Yeah, what I'm saying,
yeah,
you
it
just,
was.
yeah, you just leave it as a minus 1.
Oh, that was your question, Chris? Yes, sir. I heard you ask something, I didn't hear what it was. We're asking the same question. Good. Always a good sign. All right, question for him. Yes, sir.
At number 2, step right there, how did you just get from x minus 1 all squared to x?
I'll take the integral. This part, you talking about how did I get from here to here?
Yeah.
Yeah, if you integrate that, that's what you'll get. And you just plug in on 2 to get the rest of it.
So take the derivative of it for a -4 over x minus 1 for Scorpio, so he sees why that is, why you right. Just right up top of the board, we got some space up there, right? Y equals -4 over x minus 1. And you're gonna take the derivative of that, what's a good way to rewrite it? Yep, to the -1, right? All right. Yep, now take the derivative. And what do you get? -4 times the -1, right? No. Remember your power rule, -4 times that -1, right? -4 times the -1 is gonna be what? +4 times x minus 1 to what power? Times x minus 1 to the
Negative second.
to the what power? Correct. Which is what you said, which is 4 over, you got it. Right? So how do you get it? You could do a u sub if you wanted to. But it's really just a power rule. Rewrite it as 4 times x minus 1 to the -2. All right. Okay, good. All right, so now finally we've got the improper integrals kicked off. So on Friday you have these hyperbolic trig things that are due. They're not hard. Let me kickstart you on that. So sinh of x is the definition is that it's e to the x minus e to the minus x over 2. Cosh of x is e to the x plus e to the negative x over 2. And all the rest are defined just like the trig functions are. So, you know, hyperbolic tangent of x is sinh over cosh. So what are these functions? Look, let's look at cosh for a second. What's e to the x like? E to the x looks like this. What does e to the negative x look like? Yeah, that flipped around the other way, right? Okay? If I add those two together, well, way out here at negative infinity, I'm adding nothing to this one, right? But I'm barely adding, even really at negative 10, I'm only adding a tiny amount to it. So it's just barely going to be above this graph over here, right? Well, right here, I'm adding 1 plus 1, that's 2. And out here, again, I'm adding almost nothing. So that's e to the x plus e to the negative x. Now divide it by 2, meaning, you know, everywhere over here, take the distance from here to here, take half of it. And 2 divided by 2 is 1. So there's e to the x plus e to the negative x over 2. No rocket science there. Figure out the graph just by looking at the graphs of e to the x and e to the negative x. I don't think you need the graphs really to work the problems, but they arise from doing trigonometry on the sphere. You know, you take a sphere and you draw a triangle on it, it looks different. But if you want to do trigonometry on the sphere, you use these hyperbolic trig functions, and things don't work out quite the way they do in the plane because you bent everything. But that's not where we're going. I just want you to be able to do the grunt work associated with it. So if I was asking you to take the derivative of sinh, you just go to the definition, and then, I don't know, break it up. It's right, just break it into the little pieces till you get the derivatives of, well, now e to the x over 2 minus e to the negative x over 2. Okay, you ought to be able to take the derivative of both of those. If you can take the derivative of e to the x. If you're taking the derivative of this guy, you're back to the quotient. You want to take the derivative of this, it's the derivative of this. Well, that's the derivative of the first times the second minus the first times the derivative of the second all over the bottom squared. So what's the derivative of sinh? It's cosh. So this is cosh squared of x minus the derivative of cosh is sinh, so that's sinh squared of x all over cosh squared of x. But that's 1, because there's one of your identities you can prove is cosh squared minus sinh squared is 1. So that whole thing is 1 over cosh squared of x, which is, what's the derivative of 1 over hyperbolic cosine is hyperbolic secant. Okay, so all of these are just grunt work, making you practice your quotient rule and derivatives of e to the x and college algebra, because, you know, one of the things I ask you to show is that cosh squared of x minus sinh squared of x is 1. Well, what's cosh squared of x? Cosh squared is e to the x plus e to the negative x over 2. Square it minus what's e to the x plus e to the negative x over 2. Oops, but a minus. All squared. Well, that's just multiplying things out.
1/4 e 2x plus 2
EX, E negative X, plus E negative X, E negative 2X.
One. Yeah, you go. It's one. Anyway, hammer through it. It's just basic college algebra here. It's just basic calculus here. Remembering your trig identities, your hyperbolic trig identities. Just hammer it out, write it all up. Only 242 is extra credit because that one asks you to find a nasty inverse, and I'll just make that one extra credit instead of mandatory. But all the rest is mandatory. Yeah, you're
So whenever it says, on 240, see the sign, hyperbolic sign of x over dx, that's just asking.
Yes, ddx is just another, this ddx of sinh of x is just a different notation that means take the derivative of this here function. You got it. Yeah, I actually changed the notation just recently in the notes because I didn't like that either.
You say this was 2 presentation grades?
Yep, 2 presentation grades. Due this Friday. Your brain is up due this weekend. All right. All right, so you're good on hyperbolic functions. I don't know what else there is to tell you there. Let's see, you're supposed to take the derivatives. You know, for the inverse hyperbolics, it's back to the same thing we did for the if f of x is the inverse hyperbolic function, then apply the hyperbolic function to both sides. All right, you take a function, you apply it to its inverse function, you get back x. Now you have something you can take the derivative of. What's the derivative of sinh? Cos. What's the chain rule say? Times the derivative of the inside. What's the derivative of x? 1. So all of these problems are going to follow this basic start. Then you're going to say f prime of x is 1 over cos of f of x. Now, you don't really want f of x on the right side, so you draw a triangle, except you can't draw a triangle because these are in the sphere. But you will have proved this identity. That means that cos of x is 1 over the square root of 1 plus sinh of x squared. Add this to both sides, take the square root, we got this. Wait a minute, we knew what sinh was. Sinh was I lost my f of x, didn't I? We don't know what sinh of x is, but we do know what sinh of f of x is, right? Now let's go back. So sinh of f of x is x. Aha. 1 over square root of 1 plus x squared. So that proves that the derivative of this guy is just 1 over square root of 1 plus x squared. All right, questions any of those guys? So Brady tells me that in grading the quizzes, the problem was not identifying the technique. Y'all did a good job identifying the technique. You just died on the integration, right? So that just means there's a huge practice set in the back of section in 15.6, and you just need to be hammering through those until you can look at them and ask. Ask. You've got what? 1 more class before, 2 more classes, 3 more classes before your test on Tuesday. So just look through the problems. If there's any of them you can't work, start working them tonight. Ask tomorrow before class, and I'll start them. I'll tell you at least how to start them. If you can't see how to start them, if you know how to start them but you can't finish them, I'll be happy to help you. But practice those integrals, because you need to be able to do those 4 integrals in that amount of time, or comparable integrals like that. It's not going to be those, it's going to be some others. But you're going to see every one of those techniques on a test a week from today. So, and the only thing here is just a speed game. How fast can you identify which technique, and how fast can you whip it out? And the only thing that's going to make you fast at that is doing a bunch of them before then. And Mike's. So I'll be happy to help. Just come ask. Okay, I have a couple of quizzes. Cody, come pick up your quiz.